Now it shows only my face. Let me see.
We'll go back, stop sharing the screen.
Oh, I have to stop sharing. That's right. You told me that before. Maybe I can do this. Might work.
Okay, yeah.
Okay. So let me see. Sharing the screen. Okay. Okay. Can you? Okay. I guess you can do it. That's fine. I just want to make sure. Yeah. Okay. Okay, I guess I hope everything is running okay. I'm actually recording it with Zoom, but I cannot see if it's recording well because it's one of these buttons up there. Seems to be recording. This thing doesn't pop down easily, it just stays up there. Ah, here it is. It seems to be recording. I hope it's recording something. Okay. So let's get started then. I hope that you can really continue this mode of teaching for the rest of the semester, because I really like this mode of teaching rather than teaching online. Let's pray that we can do it this way for the rest of the semester. Any questions before I get started? Yes?
The reflection modules.
Yeah.
I don't remember if you said anything about it in class. That's for everyone or just online students?
Yeah, I would say that for in-class students, it's optional. Okay. And if you're online, you have to do it. Yes?
How have you reflected for our grades? The syllabus says that each one of them.
Yeah, I will use that like if you're in the marginal gray area between A and B, and I will use it to decide whether you should get an A, B, or B plus or something. So it is like a swing vote kind of thing. Okay, so you can do it, and it might contribute to your grade, or it may not. If you're doing really well, it doesn't matter. But if you want to do it, that's fine too. Any other questions? If not, I was not able to pace myself very well in the last two lectures. The first lecture I was going too fast. The second lecture was going too slow. And I hope you can pick up some of the materials by looking at the video record. Would be better paced in this lecture. And I hope I can breathe better too, because I just changed my mask from the other one to this one. This is Dr. Fury. If you want a good mask, I was told that Dr. Fury makes good masks. So let's look at how do we solve electrostatic problem. Before we go into magnetostatic, which is the second slide here, I like to just review the electrostatic problem. So as we say, when you let the partial t to be 0, Maxwell's equations become very simple. And for the electric field, it will be Faraday's law equals to 0. And then the other one that involves the electric field is this one, which of course can be written as epsilon E equal to rho. And in order for this equation to be satisfied, we let E equal to minus grad phi. And if you do that, then this will become divergence of epsilon grad phi equal to rho with a minus sign up front. And then you can convert this equation. If epsilon is a constant independent of space, then you can write this equation as Laplacian equal to minus rho epsilon. This is called the Poisson's equation. Okay. And oftentimes you just write this as Laplacian, but the Laplacian is just Java. There are any questions on electrostatics? I'm presuming that you have been exposed to this before in some undergraduate course. Okay. So if no questions, let's move on to look at how we solve magnetostatic problems now. In magnetostatics, we look at the other two of the four Maxwell's equations. The first Maxwell's equation that we just looked at was this one. And then I will have curl of H equals to J. Okay, if partial t is equal to 0, and then divergence of B, which is the same as divergence of mu, H equal to 0, okay? So that is electrostatic, and that is magnetostatic. Okay, so how do we solve magnetostatic problem, which are those that belong to the second row of equation? So you find that divergence of B has to be 0. And there's one immediate hint. You can choose B whose divergence is always equal to 0, and that B is given by curl of A. Because you have known a vector identity that divergence of curl of A equal to 0. Okay, divergence of curl of A equal to 0, and hence by that choice of B, the second equation above is automatically satisfied. So why is this identity true? Well, it is actually true for a very simple reason, that if you have a vector A, and if you dot it with a vector A that is crossed with something else, that is always equal to 0. It's something that you learn in vector algebra. If you take a vector A cross with something, it produces a vector that's orthogonal to A. And hence, if you dot with A itself again, it is equal to 0. You can see this identity using geometrical argument. You can also prove this identity using algebra. You can plug in the Cartesian coordinates for A and B, okay, and then go through all the algebras. For instance, you can let A be with its Cartesian components. And then you can let B likewise in its Cartesian components. And you just plug in, and if you go through all the vector algebras with dot products and cross products, you find that it's equal to 0. And using the same technique, you can prove that divergence of the curl of A equal to 0. Same algebra. It's for the same algebraic reason that this identity is true. And then we now let B equal to mu H as we did just now. And then if you look at this equation now, okay, it would be curl of, if you look at this equation now, curl of B, H, which is B over mu, which is actually curl of 1 over mu curl of A. Okay, we forget that equation because we assume B to be something of this form, so that the second equation is satisfied. And then that should be equal to J. Okay, that should be equal to J. Let me draw a line so it's not confused you. So the vector potential A is called the vector potential. Okay, the vector potential A should satisfy this equation. So given J, which is the current in the system, you're supposed to be able to find A. And then this looks rather complicated. It looks rather complicated because we have curl of 1 or mu curl of A. It turns out that this can be further simplified if mu is a constant. If mu is a constant. If mu is a constant, then you can actually take mu outside the derivative operator because it's independent of space. You can take mu outside and put it to the right-hand side. You have this curl of A equal to mu J. Got it? Okay. So we said mu and del commute. The mathematical way of saying is that mu and del commute. Okay, if you're a mathematician, you will write it this way. And this is called a commutator. And commutator means mu del minus del mu. This is equal to 0. Okay, it's the mathematician way of saying that. And then the left-hand side of that equation that we just derived can be further simplified. And this simplification again make use of the vector identity that we have just learned, which is that A cross B cross C. Okay. Does anybody remember what this is equal to?
The cap thing.
Very good. Back of the cap thing. Okay. So back of the cap thing. So it's a very good mnemonic. So you say B A dot C minus C A dot B. And the sanity check is that the vector on the right-hand side can never have any component in the A direction because it's crossed with A. Hence, the right-hand side can only be written as the linear superposition of B and C. Okay, and then you plug in the necessary components. You can also prove this identity by using vector algebra. And then you can plug in the necessary component. It doesn't matter even if A is a del operator, B is a del operator. As long as you write it with the correct vector algebra, you can show that this is equal to divergence or gradient of divergence of A minus del dot del A equals mu J. Okay, equals to mu J. And we used this identity before when we were trying to derive the wave equation from Maxwell's equation. Okay. And then we try to convert the vector wave equation into something simpler. Here is deja vu again. We have the same equation. We go from the double curl operator that we have above into that thing. But we don't have the liberty of setting one of the terms to 0. Before that, we were having an equation something like this. The double curl operator on the E field. Okay. And we say divergence of E equals to 0 because we were in a source-free region. But here we cannot arbitrarily set divergence of A to 0. We know good rhyme and reason or rhyme or reason. Okay. So we have to argue for good reasons to set divergence of A equal to 0. We call it a gauge. Why don't we assume that divergence of A equal to 0? It's something that we cannot argue logically, but it's something that we have to assume. And this assumption is called Coulomb gauge. Okay. If you assume that the solution satisfies Coulomb's gauge or Coulomb gauge, then what you have is that the equations that we had previously, one of the terms would disappear. This one would disappear. Okay, this one would disappear. Let me just blow it up again. This term will disappear. I only have this term left. And then the equation that you're left with is simpler. which is Laplacian of A equals to minus mu J. Okay. And we had this equation similar to this one before when we were solving electrostatic problem. But that equation that we had was this one. It was Laplacian of phi equal to minus rho over epsilon. Okay, that was called the Poisson's equation. And the equation of the left looks strikingly similar to the Poisson's equation, so we call it the vector Poisson's equation. Okay, they are of the same nature. And if you were to write this out explicitly, equating x, y, and z component, you actually have three equations here. The x component is equal to mu jx. And then the y component will satisfy this equation. Then the z component will satisfy this equation, okay? But there is some caution here that you cannot always do that. You cannot always take a vector equation and break into three equations like this, unless under a certain very special condition. The special condition is that Laplacian of A, which is Laplacian of x, ax, plus y, ay, plus z, az. Okay, if I assume that x hat, y hat, and z hat are all constant vectors, they're vectors independent of positions, then I can commute a Laplacian operator, which is a position operator, and write this as x hat Laplacian ax plus y hat Laplacian ay plus z hat Laplacian az. This is kosher. This is true. Okay. However, x, y, z are not constant vectors. This is not true. So you won't go and do something crazy like this, where you will say that Laplacian of A, and you would express this in cylindrical coordinate, for instance, az. I suppose you know what cylindrical coordinates are, right? Vectors in cylindrical coordinate system. Okay, and then you will have something like that. And you have three unit vectors that are different, rho hat and phi hat. Those unit vectors are not constants of position. If you imagine cylindrical coordinate system, you move about in space, the rho hat and the phi hat point in different directions, depending where you are in space. So for this line, you cannot transpose it. You cannot commute them. Only when they are in Cartesian coordinates can you transpose them. So what we have in essence is that we have three equations in Cartesian coordinates. Okay, and we know how to solve a Poisson's equation of the scalar form that we learned in electrostatic theory. We just apply the same mathematical knowledge to solve the same Poisson's equation that we have. So, like for instance, when we have this, and we know from Coulomb's law that if rho is a point charge, say if rho is a Q r minus r, let's call it r prime, okay, r minus r prime, which means that it is a point charge in space. I hope you know how to read delta functions in 3 dimensions. The delta here is a delta function in 3 dimensions, and what I want to say is that in physics, if you have something like this, that just means that it hardly occurs in electrical engineering. Okay, that's how you read the delta function, 3 dimensions. And if you have a point source, you express it in that manner. And we know what the field due to a point source is. We learned that from Coulomb's law. Okay, we know from Coulomb's law he proved many years ago that if you have a point source, a point charge Q, then it gives rise to electric field. The electric field is proportional to, I don't remember what the constant is now. And then the electric field is pointing in the r-hat direction times some constant. And then because the electric field behaves in this manner, you can also show that since the E is the gradient of the potential, you can infer that the potential should be something of this form, that the phi has to be something of 1 over r minus r prime as well. This can be written as r minus r prime squared as well, okay? So I'm a little bit sloppy there. You see what I mean? We know how to solve Poisson's equation when we have a point source on the right-hand side. We did not actually solve it. We just infer what the solution is using Coulomb's law. We infer that the electric field should be something like this, hence the potential should be something like that. It can be solved from first principle using mathematics, but it's too difficult and too long to show that. So I'm just going to use Coulomb's law to infer that the solution to Poisson's equation is something of this nature. I don't know what the constant is, and I don't remember what it is. Okay. So because of that, then I can define something called the Green's function. As we did in electrical engineering, this is the point source response. This is a point source response, and all electrical engineers know about impulse response, but impulse response is in the time domain. This is the point source response in the 3D space. Okay, so if you put a point source in space, you give rise to in all three directions. There's no causality here, unlike the time domain stuff. So you can actually work out this Green's function in closed form. This Green's function is actually going to be something like 1 over 4 pi r minus r prime. Okay. Okay, this is called a Green's function. Okay, any questions so far? I did not derive it, I just infer it from Coulomb's law. And this was derived by George Green long ago, maybe in the 1700s or 1800s. George Green is the self-educated genius. He actually, where does he live? He lived in the place where Robin Hood was on the case. Okay, do you remember where Robin Hood was? Huh? Nottingham. Nottingham, yes. Is from the same place as Robin Hood. Okay. So he derived this Green's function on his own with very little education, but this Green's function is very impactful because once you know the Green's function of the system, it's like you know the point source response or the impulse response of the system, you can find a solution due to any arbitrary sources. So any arbitrary source, as we said before, can be written as the integral of the point source with an arbitrary source, or convolution of a point source with an arbitrary source. And everybody knows this because the shifting property of the delta function. But it also has a physical meaning. The physical meaning is that the left-hand side, which is a distributed source, can be written as the right-hand side, which is the linear superposition of point sources. Can you see that? Right-hand side is just integral summation of point sources. Can you see that? Okay, so this is just a ideal of superposition. So if I know how to find the solution to one point source, I know how to find a solution to some of point sources, which is the right-hand side. So if I know how to solve the Poisson's equation with a point source, I know how to find the solution for a general source. So in other words, I can find the vector potential, okay, which is actually this equation that I have written down before. Okay, the x component of the vector potential, okay, which is here. If I know how to write this as an integral summation, I can use the idea of convolution using the idea of linear superposition, find out what a sub x is. And a sub x, using the principle of linear superposition, is just equal to minus mu over 4 pi. If you cross all the t's and dot all the i's correctly, okay, the concept is just principle of linear superposition. And this is the solution. Okay, can you see that? I essentially have solved that very complicated looking equation up there, the second line on the previous slide. I write it down by using the concept of principle of linear superposition in green function. Any questions so far? Anything that's perplexing to you that you might want to ask? No? Yes, yes.
Is there, what's underneath the negative, like negative e over 4 pi, or something in front of
Okay,
it?
that's my pen. Okay, let me try to erase it away.
Oh,
Sorry about that.
the,
Okay, it goes away. It gives rise to a serious symbol sometimes. Okay, but try to understand the physical meaning of this integral. Okay? Try to catch that, and if you catch that, then you're all set to go into something more complicated. So I can repeat this for the xyz component, and in general, I will say that vector A would just be equal to the convolution of this 3D convolution, okay, the R prime. J, I can replace J with XYZ component. And it might be a little bit confounding for you, then I jump from the scalar case to the vector case immediately, but if you go through the thought processes, it is okay. Okay, if you repeat all the XYZ components, you get the third equation. Okay. I'm just writing all three equations into one equation, XYZ component. Yes.
Is there a reason why the negative disappeared?
Oh, very good. Okay, very good. The negative shouldn't have disappeared. Let me make sure I have this right. Okay. I want to make sure that I have this right. Let me check my lecture notes. Okay. I always have problem with my signs. I always make sign errors. Okay, that sign shouldn't be there because the Green's function is defined to be this. If I go back to the previous slide, okay, the Green's function is defined to be this without the sign, whereas on the right hand side it has a minus sign there. Okay, so finally, if you dot out the i's and cross the t's, then you shouldn't have a minus sign. Okay. Yes.
so to clarify, you're doing a convolution between the source J and the solution for a single point source. Which
That's
is the
right.
one above.
Right, which is called a Green's function. I can also write this as a Green function convolution. I could also have written this as mu K R prime G R minus R prime. Okay, or if you want to write it abstractly, you might want to write this as J convolved with G. Okay. Okay. So with A being found, I can find my B. B is just curl of A. So I have to, however, emphasize the fact that all the things lead to this point because I have assumed that divergence of A equals to 0, or I have used Coulomb's gauge. Otherwise, things wouldn't be that simple. So why do we need Coulomb's gauge? We need Coulomb's gauge for the very simple reason that if I use this to define what the B field is, that if I have two potential, vector potential A prime, and they're related to each other by just a gradient. They are just related to each other by the gradient. Okay. And you can see that curl of the gradient is equal to 0. Okay, curl of a gradient is equal to 0 for the very similar reason that B cross B equal to 0. Okay, go to the algebra, you can show that in the case. Then what it means is that if I were to take the curl of this vector potential on the left-hand side, both of them will give me B. So, which means that A is not unique. I can find another vector potential called A prime, and if you take its curl, it still gives you the same B. So A is not unique. That is, if we never stipulate the Coulomb's gauge, okay? If we stipulate the Coulomb's gauge, we will be able to distinguish who the real McCoy is. Okay, so if I were to take the divergence of A prime, I will have this. And then I will have Laplacian of psi. And if I impose Coulomb's gauge on both of these potentials that I have guessed, A prime and A, and impose them to satisfy Coulomb's gauge, then both of them have to satisfy this equation. This would imply that Laplacian of phi has to be 0. This is only possible if Laplacian of phi equals to 0. It turns out that you can prove, which is a rather tedious proof, that if the Laplacian of something equals to 0, that something has to be 0. If that function goes to 0 and infinity. Okay. If I further impose that phi tends to 0 when r tends to infinity, then it implies that phi equals to 0. Which means that impose Coulomb's gauge on all the potentials that I have found, they cannot be different potentials. Which means that the phi that I have here has to be 0. So this A and this A prime must be the same because this can only be 0 if I impose Coulomb's gauge. If both of them satisfy Coulomb's gauge, that phi has to be 0. Can you see the logic here? Okay, good. I see some nodding heads. I suppose you caught it. Okay. So this is also very similar in vector algebra that if I have a vector A, and if I only stipulate the cross of A with B equals to C, that does not uniquely define what A is. Okay, it doesn't have to be a del operator. Just take any vector that you want. If I take any vector A cross with B and stipulate this to be C, I don't know what A is. Can you see this geometrically? If you can see geometrically, I can do some more and assume that B is pointing in this direction. Okay, I divide my A into two components. One component is parallel to D. Okay, parallel to D. The other component is perpendicular to D. Okay, any vector B, I need arbitrary vector A. I can always break into two components, one pointing in B, one that is orthogonal to D. Okay, and you can see that if I were to cross B with A, then I will get D cross with A parallel plus D cross with A perp. But sheer definition of what A parallel is and A perp is, what is D crossing with A parallel? 0, right? 0, and then, so if you were just to take the curve of A with D, you can only have this information. You can only pick up information on the perp of A. And hence, A cannot be uniquely determined. Okay? You need to do something more than this. So if I were to impose this condition, then this would only pick up the parallel component, because D perp, D dotting with that component gives me 0. Okay, and the second equation will give me a way of determining A parallel. So it's the same kind of idea. That's what Coulomb's gauge is. Okay. Any questions? So if no questions, let's go beyond magnetostatic and study something about boundary conditions. Okay, boundary conditions. Boundary conditions are rather important. You need boundary conditions to solve an ordinary differential equation, and you probably have heard about that before or learned that before. That is that you need this in a boundary value problem. Say if you were to solve a very simple ODE, you might have come across this ODE before. You cannot solve this ODE without telling me what boundary condition you want the solution to satisfy. Okay, the solution will not be unique. However, if you tell me this ODE, I want the boundary condition that y x is equal to 0, that x is equal to 0 and A, and L maybe 0 and L. Then that is some of a boundary condition. This is called boundary value problem. And you can solve this, and probably all of you know that this is the wave equation. So the solution of this wave equation would be something like this, something that satisfies the boundary condition. Is this, or I can do the second mode. Okay, the third mode. You need boundary conditions to get a unique solution for ODE. Okay, but we're going to learn more boundary conditions in this lecture. Boundary conditions of the complicated kind. Let's assume that we talk about electrostatics first. In electrostatics, the equation that we have learned is actually Poisson's equation. Okay, this is Poisson's equation. This is actually a three-dimensional partial differential equation, which we call PDEs. Partial differential equation. So the boundary condition can be in 3D space. It's too complicated for us to imagine, but let's imagine a one-dimensional problem first. And for that very simple one-dimensional problem, let's assume that epsilon in general could be a function of x, y, and z, but for simplicity, I'm going to assume that epsilon is a function of epsilon, a one-dimensional epsilon. So it will look something like this. It's a dielectric constant. You can think of a dielectric constant that changes only in the x direction. It might be a dielectric slab or something, and it changes in that manner. And that there's a discontinuity at x0, x equal to x0. There's a discontinuity in the dielectric constant. Let's make life a little bit more complicated. Let's assume that there's a charge density here. That the right-hand side rho of x is actually rho of s times delta x minus x naught. Okay. The charge density is a delta function in x, and that delta function is located at x naught, which is where I put the discontinuity is. So imagine that this is a charge density. I'm doing everything in 3D, so this will be a charge sheet. Okay, there will be a charge sheet at that location, and that charge sheet would be at that location. And what kind of boundary conditions would I have to have in order to solve this equation? Well, if I look at this equation in one dimension, Poisson's equation in one dimension will look something like this. Okay, and the charge has only one-dimensional distribution, is a delta function. And then I ask myself, I stare at this equation very hard. The right-hand side is singular. What is the singularity that you see on the right-hand side? You see a singularity there, or you do not? Or you just see words? See anything there on the right-hand side? Right-hand side is a delta function. We usually call that a singularity because it goes to infinity. Anything that goes to infinity is called singularity in mathematics. So right-hand side, we have a singularity at x equals x naught. Okay? And right-hand side is the derivative of functions. Okay, derivative of functions. So if I were to ask you, if I were to take the derivative of this function, what does that function have to be in order that when I take its derivative, it gives me a delta function on the right-hand side? We know, very good. We know good electrical engineers know this. You must be a good electrical engineer. Okay. If you differentiate the step function, you get a delta function. So what I put there as an under brace must be a step function. Okay. So if I were to sketch this part, then this part must be something, and my sketch might be wrong. Okay. This part might look something like this. It must have a step discontinuity. Okay. But if something gives rise to something, okay, so epsilon d dx, phi gave me this. So if I were to sketch phi, how would it look like? How would phi look like? What gives me a step function when I differentiate it? If I differentiate something, it gives me a step function in return. What is that function looking like? Usually we call it ramp, okay? A ramp with two different slopes, for instance, because if you differentiate something with a linear slope, you get a constant. If you have something that has two constants, it must be two ramp. Okay, so it might look something like this. Okay, so the third function has a special property that it is continuous. There's no more step discontinuity. We usually call this function to be a smooth function mathematically. Okay, So by just eyeballing this equation, I immediately see that phi of x is a smooth function. How smooth must it be? It cannot be very, very smooth because when I differentiate 2 times, I get it, the other function. So it must have a ramp function with this continuous slope. Okay. So these are the kind of insight that we get by just staring at these equations. Okay, but how do we show this mathematically? Well, so if I look at this equation, I can derive this mathematically by integrating this equation. Say if I integrate this equation from x naught minus delta to x naught plus delta, I just take this equation, go back to my previous figure, where x naught was the location of my singularity or the state discontinuity. So what I have then is that if I were to integrate the left-hand side, I will have that. And then the right-hand side, if you were to integrate over the interval that picks up the delta function, I'll just get a constant. Agree? I will just get a constant because the window of integration will just pick this up, and then the right-hand side becomes rho sub s. Okay. And then the left-hand side is an exact derivative. So you can integrate it exactly, and if you do things correctly, then you will get this equation. At the 2 limits, x naught minus delta, x naught plus delta. And this is the mathematical way of saying that the first function that I have has a state discontinuity, and that state discontinuity is given by minus rho sub s. And if you were to integrate this equation one more time, you'll find that phi of x is a smooth function. So those are how boundary conditions are derived. And you probably know that Ex is equal to minus d dx phi of x. Okay. And if you apply this boundary condition that we have just learned, okay, you will get that dx minus, let me see what notation it is, x plus, I use x minus. Okay, you get this kind of boundary condition where x minus and x plus are a way of denoting something immediately to the right of x naught and immediately to the left of x naught. So there's a jump discontinuity in the electric flux, and this electric flux can also be written in a different manner. That you can say that dx1 minus dx2 is the surface charge density. It's something you probably have learned before as an undergraduate EN course. I'm just arguing to arrive at this boundary condition in a different manner. Okay, so you can see that boundary conditions are buried in the PDEs or the ODEs. So Maxwell's equations are PDEs. So whatever boundary conditions we have are also buried in it. We've seen that by staring at an ODE, you can see the boundary condition. By the same token, by staring hard at Maxwell's equations, you can also see the boundary conditions. Let's see how we can do that. Well, let's look at Faraday's law. Faraday's law says that curl of E is equal to partial B partial T. Okay, it's hard to see the boundary condition by this staring at this 3-dimensional partial differential equation. But we do Conductive experiments and start to project this equation into a simpler space. We can draw a picture and say that Well, let's have an interface. And in this interface, I might have two different media. And then at this interface, let me call this direction Y. I give this a local coordinate system. And then I call this direction X. Okay, I give this a local coordinate system. And then I give this unit vector here. I use hat to denote a unit vector. That unit vector is just X hat. And then I would have another unit vector Y hat. And then there might be another unit vector Z hat pointing out of the paper. Okay. So I'm going to write Maxwell's equation using this local coordinate system in Cartesian form. So curl of E expressed in terms of local coordinate system. I can write down my curl. No, that's not right. Okay, I shouldn't put this in yet. So I can do this curl of X EX plus Y EY. Okay, and then you can do other cross products. You know how to use a distributive law and cross them out term by term. And that you know how to do. You don't have to draw a determinant diagram. And then you will see that Z partial X EY plus Y hat partial X EZ minus Z hat partial Y X plus X hat partial Y EZ. Okay. And then you can see that this quantity, if this is a Y direction, okay, partial Y EX must be finite. Okay, partial Y EX must be finite because the right-hand side of this equation of Faraday's law is finite. There's no singularities on the right side. Assume that all the D fields are smooth. So if I look at the left-hand side, every term that I have on the left-hand side must give me a finite number. So if I just look at one of the terms, E sub X, for instance, the differentiation of E sub X in the Y direction must be finite. Can you see that? So what does it mean? It means that E sub X must be a smooth function in the Y direction. It cannot be discontinuous because the right-hand side is finite. Similarly, I can also look at E sub Z, okay, and its derivative in the Y direction must also be finite because I have nothing singular on the left, on the right-hand side. And then the partial X and partial Y, those are all regular since I don't have any possibility of having any singularity there. I'm assuming that the discontinuity can only exist across an interface. So discontinuity cannot exist in the X direction. And this two will not give me anything that is singular. Okay. So you can see that just by staring at this equation, E sub X must be smooth. And then E sub Z must be smooth. That means that they are all tangential components at the interface. Tangential component of the electric field must be smooth or continuous. Okay, so essentially by just staring at this equation, I get the boundary condition that you often get in the textbook, which is that the tangential component of the electric field is smooth, okay, or continuous. Okay, let's look at, I seem to not be able to write here. Okay, let's look at Gauss law then. Gauss law, yes.
On that previous slide, isn't there a couple of terms that cancel out in the cross product that you were doing. Just looking in the lecture notes, delta 2. Delta 2,
Which two constants?
the one on the right and the one.
The last one?
Yeah, the last one, and then the one that you have underlined. Like I know the y hat and x hat, but in the lecture notes it just shows two terms.
I think in the lecture notes, I only assume one field components rather than the two field components. Here, I assume that I have EX and EZ. Or EX and EY, right? Sorry, this shouldn't be there. EX and EY. Okay, I assume that EX and EY, which means that I have electric field pointing in the X direction and the Y direction. And in lecture note, I don't remember what I have now, but I might have EZ as well. Okay, I might have put in an EZ as well. That's why when I go to the second line, I have the Z components as well. Okay, but now never mind about this. I wrote it without error in the lecture notes. Okay, what I wrote down, I might have errors here. Okay, so let's go to Gauss law. Gauss law is this: divergence of B equal to rho. And again, I can stare at this equation and see the boundary conditions. Okay, how do I do that? I have a local coordinate system. I would have assumed that my X direction is pointing in this direction, and then my Z direction is pointing in this direction, for instance. And then my Y direction is pointing out of the paper. Okay. And then I can call this equal to T1 hat, and this is equal to T2 hat, for instance, two tangential components. And then I can write my divergence of B in a local coordinate system. It will be equal to this plus this plus partial Z dz. And then the right-hand side, let's assume that I have a surface charge sheet on the right-hand side. And I will write this as equal to rho S delta Z. So there is a sheet of charges localized at the interface alone. And then if I look at this thing, there's no possibility for this to produce a delta function. There's no possibility for this to produce a delta function. The only term that can produce a delta function on the right-hand side is the last term, which means that jump discontinuity must exist in B sub Z if I have a charge singularity of delta Z on the right-hand side. So it means that dz must be discontinuous. This must be true. Okay, this must be true. And then you will get the boundary condition that you usually see from textbooks, that the normal component of the electric flux is proportional to the surface charge density, which is something that we can arrive at by just staring at the equations and trying to figure out what kind of jump discontinuities that we can have. Okay, you can do the same with Ampere's law. Okay, this is Ampere's law. And again, you can have an interface. You assume that there is a current J at this interface that flows only along the surface, and it is localized in the z direction. Let's assume that this is the z axis. Okay, and then you can work things out and saying that the only way that this current sheet could be a delta function is that there's some jump discontinuity in the tangential component of the H field in that direction, so that when you differentiate it, you get a delta function. So by going through that kind of argument, you will arrive at this kind of boundary condition. Okay, the tangential component of the magnetic field, if it has a jump discontinuity, must be proportional to the current sheet that resides at the interface. And similarly, you can go to Gauss laws too. The divergence of B equal to 0, and then you get n dot B1 minus B2 equal to 0. Okay, you get this to be true. Okay, any questions on boundary conditions? So the lesson learned here is that boundary conditions are entirely embedded in the PDEs that the field satisfies. Okay, and you can eyeball the PDEs and arrive at the correct boundary conditions if you know how. Hopefully, after this, you know how to eyeball the PDEs and know what the boundary conditions should be. Let's go and derive Gauss law next. We have enough knowledge now to derive Gauss law. Why don't we try to do that? Gauss law is a law that relates the magnetic field due to a current J. If you have a current I flowing in the wire, and that current will produce a B or an H, and that H is related to the current by an integral. This law was experimentally derived years ago, but we're going to show you that you can actually derive this law using mathematics. Okay. And this is a current, where did it go? This is the current element that we are talking about. So we can always break this current element into tiny elements and then calculate what the B field around it should be. So this is essentially a magnetostatic problem. And we have learned enough about magnetostatic problem in Green's function. And we have the mathematical tools to actually derive Gauss law. So we learned that in magnetostatic, curl of H is equal to J, and then divergence of B equal to 0. And then, as we said before, if we go through all the math correctly, we show that the Laplacian of the vector potential A is equal to minus mu J. And then you can actually now derive A from J. Okay. A, of course, once you know A, curl of A equals to B. That is how we solve the magnetostatic problem. And we can use the Green's function method, as we said before. If you know the Green's function of this problem, or due to this delta function on the right-hand side, which we know the solution of, G of R prime is 1 over 4 pi R minus R prime. We never derive this Green's function. It can actually be derived, but we just infer it from Coulomb's law. So, well, then we further conclude that the vector potential A is mu over 4 pi, the convolution of the current, dV prime, R minus R prime. Okay, I'm going to use the R prime, dV prime, and sometimes some textbook will use the cube R. Okay, interchangeably. They all mean three-dimensional integrals. Okay, all these are used interchangeably. in different textbooks. Okay, so I'm going to use this equation to find the magnetic field due to a small current element that we have in the previous slide. And that magnetic field, I first write it down as a vector potential first. The incremental vector potential due to that small current element that I have can be written as J R prime delta V prime over R minus R prime. Okay. Let's assume that I have just one current element. And that current element will produce a tiny vector potential contribution, which I call incremental vector potential. And that will be given by this integral over here. Okay. And that my J, I can write it down. Okay, my J delta V prime can be written down as A hat I. Sorry. L hat I. L hat is a vector that points in the direction of the current element. Okay, L hat I divided by delta A. This gives me the current density. Current density is measured in terms of amperes per meter squared. So I take the current point in the L hat direction and then divided by the cross-sectional area of the wire. This gives me the current density. And then delta V is the volume of the current element. It will be given by delta A, delta L prime. And this is my delta V prime. Okay, and if I look at this thing carefully, I can actually write it as equal to the delta A would cancel each other. I can write it as I delta L prime L hat. Okay, so I can simplify this integral and say that the incremental B, which is given by curl of the incremental A. Again, incremental A is given by this. And if I plug in everything correctly, then the curl of mu I delta L prime over 4 pi R minus R prime, and then equals to mu I. Okay, this part I have to explain a little bit. I have to explain a little bit why it becomes like that. I have two coordinate systems here. One is R prime, the other one is R. R is the location of the observation point. R prime is the location of the source point. So in this expression here, or the previous expression, R prime is source point. R is, or sometimes we call it field point, observation point, of the point you evaluate the field. And if you write this out in detail, this R minus R prime would be something like, in Cartesian coordinates, x minus x prime squared plus y minus y prime squared plus z minus z prime squared. R minus R prime magnitude is just a distance between these 2 points, R and R prime. And if you write it out in Cartesian coordinates, that would be what it should be. But this del, look at this del is taken out from the outside. And which coordinate system does the del operate on? R or R prime? Yes? Which coordinate system should Del operate on? Very good. The field point. Okay. This Del should only operate on this X prime and Z. X prime, Y prime, Z prime are the source point. Okay, that is something that students often get confused with after a while and get things messed up. So when you take these derivatives, okay, which you, yes? Okay, the last point I want to emphasize is that this Del operator operates on A of R. A of R, R is the field point on the observation point. R prime is the source point. Okay, so when you take this inside, then you have the confusion of R and R prime here. You don't know which to operate on. And this Del should only operate on R, not R prime. And if you write it out explicitly, okay, this function, which is rather complicated looking, if you write it in Cartesian coding, the derivative operator should only operate on the unprimed coordinate system. And if you do this carefully, of course, these are high school algebra, high school calculus. And if you differentiate things correctly, you actually can get some nice answer. I don't think I will go through the algebra. Okay, if you go through the algebra, which is detailed in the lecture notes, you will find that the incremental B that you have is something like mu I over 4 pi delta R prime crossing with 1 over R squared R hat. R hat is a unit vector between, if this is the source, this is the field, this is the source. R hat is just a unit vector between these two things. Okay, if you work out the details, you will have this, and then you will have delta H being equal to, because H mu delta H is delta B. Okay, if you work this out, then you will find that delta H is I delta L prime over 4 pi 1 over R squared cross with R hat. And if you now convert this into an integral, you find that the magnetic field H of R is the integral summation of all these incremental values. Okay, crossing with R over 4 pi R squared. This is called Savard's law. Okay. Okay. Any questions so far on the derivation of the Savard's law? The details are actually in the devil. The devil, what is it? The detail is in the devil. The devil is in the detail. Okay. The devil is in the detail. You go and work it out. Okay. So for the last few minutes, I'd like to talk about boundary conditions for conductive medium. We have derived all these boundary conditions, but when you have a conductive medium, you have this current continuity equation, and then your J, okay, your J is equal to sigma E in a conductive medium. And this equation can be derived from Maxwell's equations. Okay, start with Ampere's law. And then you can also use Gauss law for charges. You can derive this continuity equation. And then again, you can go through the argument that this has to be finite. The right-hand side is finite, so derivative of the J must be finite. And you can arrive quite easily just by eyeballing that equation that the normal component of the current must be 0. Okay, the normal component of the current must be 0, and then if you put in this one, you will get sigma E1 minus sigma E2, sigma 1 E1, sigma 2 E2 must be 0, which means that the current, the normal component of the current must be continuous at a conductive interface. If you have two media, such as this one, the normal component of the current must be continuous. However, you might wonder why, if this is in contradiction with what we found previously. We found that from Gauss's law that this is true. We just found this boundary condition not too long ago. So it seems that the two boundary conditions are not compatible with each other. Okay. But they will not be compatible with each other if there's no surface charge rho sub s at the interface. Okay. So what it means is that if you have a conductive medium, and if there's a current flow from one conductive medium to the other one, there must be surface charge accumulation at the interface. This is often found in semiconductor materials. Semiconductor materials are both conductive as well as having a dielectric constant. So if the current flows across that interface, you have to have surface charges. It's something that you have to keep in mind. Okay. I think I will stop here since I'm running out of time. Are there any questions before we stop? So supposed to be on Brightspace, but I can also email them to you if you want. Okay, email you the homework, or you want to go to Brightspace to download them. Which is the preferred way of receiving the homework? By email from me, or you go to Brightspace to download? Brightspace is better for you? Okay, good. Okay, see you on Thursday then.